Singh, and this is my first physics lab regarding constant velocity. And so the purpose of this project is to analyze the motion of an object moving at a constant speed and then creating a computational model. And we seek to validate the fundamental physics concepts of the constant speed motion and using empirical evidence to support the Newton's second law of motion or the momentum principle. Because there's no net force being applied, that means there's no disturbance to the object, and in our case it's moving at a constant velocity. So because there's a net force, it'll keep moving at that constant velocity as we predict, and we'll study that more in the model. And this carries on to Newton's second law as well, which is F equals ma. Because there is no force being applied, that means, and with mass being constant, that means acceleration is zero. So if there's no acceleration, that means there's no change in velocity, which means there's a constant velocity. So these both go hand in hand, and the two equations we'll use are the position update equation. So position final, RF equals position initial, plus the average velocity times the change in time. And then the final velocity equals the net force times the average the change in time over mass plus v initial. Because net force is zero, there will be no change in velocity, so Vf will equal Vi. And we'll see that more in the code. And so the diagram of forces for our thing, here's a side view of it. There's a normal force and gravity applied in both situations, the initial movement and the constant velocity phase of the object. But there's an applied force at the start, and then during its constant velocity phase, there is no applied force. There's zero net force on the object, so it's just moving at one speed. And so a brief preview is that there's a distinction between the observed and the computed, with different r squares and different slopes, but we'll see some similarities and understand what the differences are. And now we'll move to tracker and observe the system, which is the track that the mobile is on, the wheeled mobile, and then the earth. And our focus is on this object, which is moving at a constant speed between a time interval. We can see its movement on the side, and we can watch as we track it along the course. So it just moves along, and it builds the data as it goes, and it builds a line that we can then use to see, to measure its how accurate this line is and how linear it is. And with this GlowScript code, we can look at how we've adjusted it to fit the initial equations that we established earlier on. So the position updating and the velocity updating, because you have F net is zero as defined here, the velocity stays constant. We can look at the initial vector for the average velocity, only 0.307 meters per second, which is calculated using the position update formula. And then when this runs, we see a line being formed with a linear movement and the data at the bottom. And we have one column that shows the time between 0 and 1.24 seconds. As we can see on the graph, time in seconds from 0 to 0 at 1.24. Then on the y-axis, we have the different data collected, the predicted and the observed, and that's shown on the graph. The blue line represents the observed movement, and the orange line represents the computed movement with the GlowScript model. We can see the r squares of each line, and it's an r squared of 1 for the observed movement, and an r squared of 0.9967 for the computed. The velocity seems to be constant in both the predicted and observed, which relates to the initial assumption that because there's a constant force, the velocity will not be changed because acceleration is zero. And so the r squared of the line of best fit for the observed model was off by a factor of 0.0034. And the observed wheel mobile did not travel at a perfectly linear rate. There were some disturbances which need to be accounted for. So the conclusion is that the observed velocity exceeded the computed velocity, and that may be attributed to the limitations in the position of the measurement instruments or errors. Another reason could be that we didn't account for external factors or conditions that were in the computational model, which led to the observed being a bit faster than the computed model. There could have been things on the track that caused that to occur. And so what if we flip the axes? Will there be direction change? So for instance, if the object was moving in the positive x direction, it would then appear to move in the negative x direction and vice versa. Same thing with the y-axis. And then if there was speed conservation though, so the magnitude of the velocity or the speed would not be altered. So both the observed and the computed velocities would maintain their original values, and then their signs would be inverted because of the axis flip though. So what does it mean? The number of push and pulls. A zero net force can result from various combinations of forces, and so we don't really know exactly how many push and pulls there are, because there could be different magnitudes, or it could be a single balance force or a system. But these specific forces involved would require detailed analysis of all the exact forces and a much more comprehensive look at it. But yeah.